to section 3.2. This section is going to be split into two sections. One is going to be and problems, and one is going to be at least problems. So you'll see two homework sets. They'll both be labeled 3.2. We'll take two separate days to cover them. What I'm going to do in this whole entire course, I'm trying to take these problems that you encounter and simplify them by helping you look for target words that tell you what kind of problem it is. So when I say these are and problems, that's your target word that you're looking for. So for example, if I say, what's the probability that I'm playing cards and I draw a king and a queen? That and connector is what tells you what kind of problem it is. So we're going to walk through how to set these up and how to solve these. Before we start, I want to review this idea of the complement of an event, just to make sure that we're all on board with that. So the complement is a math way of saying the other part or the opposite. So if I say the probability that it's going to rain today is 10%, then the complement is the probability that it's not going to rain. It's the rest of the probability that makes up that full 100%. So the probability of no rain is going to be 90%. And when you're doing complements, they should always add to a total of 100% or 1 or a fraction like 15 out of 15, depending on what your format is. The fraction, if you're in fraction form, it should end up so that the top adds up to the same as the bottom. So as an example, if I say the probability that it rains in a given week is 2 days out of 7, then the complement of no rain is going to be 5 out of 7. See, if you add those two up, the 2 and the 5 add to 7 out of 7. So 7 out of 7 is 100%. Or if we're looking in decimals, if I say the probability of rain is 0.220, remember that's 20%, but you can look at it as a decimal. The probability of no rain is going to be 0.80. And those add up to equal 1, which is your decimal equivalent of 100%. So we're going to be using that in the next couple sections. So I just want to make sure that you're comfortable with that. Now, vocab. Vocab for this section, the two words that you need to understand are independent and dependent. And these words mean what you think they would mean. If you are independently living, that means that you're on your own. You don't have ties to anybody else, like financially. What you do doesn't depend on somebody else. A dependent, they call children dependents because they're tied to their parents, and whatever their parents does influences the other. So this idea of independent and dependent has to do with influence. So in the context of probability, like if I talk about the probability of it raining and the probability of owning a dog, these two ideas are not dependent on one another. If it rains and owning a dog, they don't have any correlation. They don't have any ties. So we would call this independent. But let's say if I'm talking about whether it's going to rain and whether I'm going to bring an umbrella to work, those ideas would be dependent, because the higher the chance of rain, the higher the chance of me bringing an umbrella. They're tied in some way. And it doesn't have to be a strong correlation. It's just if there is any influence on one or the other. Ideas that we talk about in probability a lot are like rolling dice and drawing cards. If I roll a die and I draw a card, those are independent events. They don't influence each other. Now, but here's another example. Let's say we're playing cards and I'm going to deal out cards to everybody at the table. That's actually a dependent event, because what card I get influences the chances of what card you get. So let's say I deal myself a queen. There's now less queens in the deck, and that's going to influence the probability of you also getting a queen. So if I'm playing cards, I could look at my hand and say, "Hey, I've got 3 queens in my hand. The probability is low that anybody else at the table has a queen because there's only 1 left in the deck and I have 3 of them." So that kind of idea is those are dependent ideas. Next, we need to talk about these symbols. This is this symbol. Remember, P is probability. And then I'm just using B and A as examples of 2 events. So one event, and then there's this vertical bar in between, and then another event. The way we say this is the probability of B given A. This given is what this bar, how you say that bar, that's what that means. And what this means is, like, let's go back to our card playing example. The probability of you getting a queen is 4 out of 52. That's how many queens there are, and there's 52 cards in a deck. We're going to do some card examples, so let's write this down because some people aren't familiar with cards. In a standard deck of cards, there's 52 cards. There are 4 suits. These are going to be hearts, spades, clubs, and diamonds. And there's 13 cards of each suit. And then there are 4 cards of each type. And those types start at ace, and then they go 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then they go king, these are not in order, king, queen, and jack. Okay, so there's all of those numbers in the deck. There's like 4 aces, one of each suit. There's 4 twos, there's 4 threes, there's 4 fours. So if I ask you, what's the probability of drawing a queen? You would say, how many ways can it happen over the total? Well, there's 4 queens over the total 52 cards. That's your probability of a queen. But then if I said, what's the probability of getting a queen given that I have 3 queens? So I've already dealt myself 3 queens, and now I want to know what's the probability that you now get a queen. Well, what's happened is I've taken 3 of those queens out of the deck. So how many queens are there now? There's only 1 left in the deck out of 52. So you see how that changes. Like in a dependent event, the probability of something happening changes given what's happened before. That's the idea of that notation. Now, if you're looking at a table, which often happens in like psychology and different studies, they have tables of data. So let's say we have a table here, and we're gonna look at the number of men and the number of women who have a dog and a cat. Okay. Like, we're just measuring those. Yeah, let's not think about who has both. Okay, so we have a sample of people who have just one or the other. Okay, this is the number of men who have dogs. We're going to say this is going to be 10, and this is going to be 30, this is going to be 20, and this is going to be 40, say, just to keep the numbers easy. So then we've got totals. So there's 30 total dogs in this study. There's 4, 5, 6, 70 total cats. And there's 40 men measured. And there's 60 women. And so total, there's 100. So this is usually how these tables are. These outside columns here and here are totals of the numbers in between. So I could ask you, what's the probability that I take this group of people and I randomly select a man? You did these in your section 3-1 problem. So you go, okay, how many men in the study? Well, that's going to be 40 over the total, which is 100. So the probability that I randomly select a man is going to be 40 over 100. We could reduce that, but just for sake of time, okay? But now I can ask you, what's the probability that I select a man given that they own a dog? So what this does is it says, I don't want you to any longer look at anybody who owns a cat. This is what right here, this second part, we kind of read it backwards. The second part is the restriction. So what I do in a table situation, if I say, here's a dog, okay, then I go up to my table and I look only at the dog information. So I am completely eliminating that cat column and I'm only looking at dogs. Now I'm going to answer the question, what's the probability that I select a man? How many are there? Well, in this purple column, there's only 10 men. And what are the total amount of dog owners, which is the only people that I'm looking at, is 30. So it's restricted to the 30. It's no longer 100. The total changes again because we're only looking at dog owners. Okay, similarly, I could ask you, what's the probability? Let's just do the same thing but backwards. What's the probability that I select a dog owner given that they're a man? Now what that does, let's use a different color so we can track. Now it restricts me to only men. So I'm going to go up here and now I'm going to circle this row. You see that right there? I'm not looking at the dogs. I'm not looking at the whole table. I'm only looking at the men column. And then I'm going to select how many dogs are only in that orange column, and only the orange column gives me the total. So here I'm going to go, there's 10 dog owners that are men over 40 total men. So this total on the bottom should always correlate to this second part. How many here in the pink, how many dog owners are there, and here how many men are there. All right, so that's how you do given that's, either in fraction form or table form. You'll have a couple of those. And now we're getting to the main event, these and problems. The probability of event A and event B happening. So there's two things happening. That's unique to these problems. There's two things happening. And they're connected by the word and. The notation for that in math language, we write probability of A and then an upside down U with no tail. So it's just like a little hill, and then B. That means probability of A and B. And the formula for this is we're going to take the probability of the first thing, which is probability of A, and we're going to multiply it by the probability of B given A. So you're going to adjust for what happened in A and then multiply it by the probability of B. Now, why do we care about, let's tie these all together. Why do we care about independent and dependent? Because if A and B are independent, so they don't influence each other, then the probability of B given A is just the probability of B. Because B doesn't depend on A. So there's no, like, this A restriction doesn't actually restrict B. So let's do an example. If I have the probability that it rains is 30%, and the probability that I own a dog is 20%, what's the probability that on one day it rains and that I randomly select somebody that owns a dog? So the way I do an and problem is I first take the probability of the first thing, which is the probability it rains. Now remember, when we're in percentages, we have to change to decimals because we never multiply with percentages. So 30% changes to 0.3 and 20% changes to 0.2. So 0.3 is my probability that it rains, right there. And means times. That's the symbol for times is a dot. The probability of me owning a dog given that it rains. Now, if they're independent, the rain isn't influencing, it's not changing this percentage of owning a dog. So I just simply multiply by 0.2. So this problem becomes 0.3 times 0.2. 0.06. So the probability in this situation that it rains, I'm going to do two things. I want to know if it's going to rain, and then I'm going to randomly select a person, and I want to know if when I do this, I select a day that it rains and a person who owns a dog. That's going to be 0.06. Now think about this number. This is a 6% chance that both of these things happen. That makes sense, right? Because look at the percentages. It's only a 30% chance that it rains, and it's a 20% that I select a dog owner. Those are both pretty low. And if I have to have both of them happening, the more things that you have to have happen in a row, the less likely it is to happen. So, like, let's take example. Say you have children in your home. The probability that I have a boy versus a girl is just 50-50, right? But what's the probability that I have 5 boys? It gets less and less likely the more events that I stack up that have to happen in a row. Why? Because I'm multiplying fractions together. And when you multiply fractions, the numbers get smaller. All right, so let's do that problem. The probability, let's not do 5. Let's just do, what's the probability that I have 3 boys? Now, the language there doesn't have the and in it, but it's implied. Listen to it this way. What's the probability that I birth a boy and a boy and a boy? All right, so there's ands connecting those events. I'm not talking about or anything else. Like I'm saying and in a row. So this is going to be 3 events. Sometimes I like to do this. There's going to be 3 things that I fill in because 3 things are happening. It's an and problem, so I'm going to hook them together with multiplication. And then I just go one by one. What's the probability that you have a boy? How many ways out of how many total? 1 out of 2. Now, what's the probability you have a boy? This is an independent event. The previous event does not affect my chances for this, so I'm just simply multiplying these together. It's again 1/2. And then what's the probability that I have another boy? 1/2. So multiply these all together, you get 1 out of 8. See how that percentage went down from 1/2 to 1/8? So it's less likely that that happens. Let's take another example. Let's look at some cards. So let's say that I want to know, this is our deck of cards. I've got numbers. I've got 1 through 6. And I've got animals on each one. I've got fish on 6 of them, cats on 6 of them, birds on 6 of them, and dogs on 6 of them. So I want to know what's the probability. I'm going to draw 2 cards. And I'm not going to replace the cards. So I'm going to draw one and keep it in my hand and then draw another. This phrase, without replacement, is a key phrase that tells you if the events are going to be independent or dependent. So if I'm not going to replace the card, this is going to be a dependent event. Because me taking a card out of the deck is going to change the probability of the next card. Think about the queen example we talked about earlier. That was a dependent situation. So let's say that I want to know what's the probability that I draw a fish card and then a bird card. Now remember that there's 6 of each. So the first thing that I'm going to do is just look at the fish card. What's the probability that I get a fish? This is just a 3-1 set question, a simple probability. How many are there over the total? So there's 6 fish out of the total, which we have 6 options times 4 is 24. There's 24 total cards. So my probability of drawing a fish is 6 out of 24. That's how many there are out of the total. Now what I want you to think for the second event is what you assume that what you wanted to happen at first actually did happen. So I wanted a fish. So let's say I drew a fish. So I'm going to come over here to our cards and I'm going to X out one of these fishes. Now, I don't know if it was that one or the other one. It doesn't matter. Just one of them's gone. And so that affects now my second event. So my second event is, what's the probability that I'm going to draw a bird? Well, there's still 6 birds in the deck. So I still have 6 options, but what changes is the total. So now instead of 24 cards, there's 23 cards. And then you multiply those. So the fish probability is 6 out of 24. The bird probability is 6 out of 23. And we're going to multiply those together. This second event right here, this bird, this is, we actually just mechanically calculated the probability of B given A. So that given A, what we did was we actually mechanically crossed out the fish and figured out what this new probability is. So a lot of times when I'm talking about and problems, I don't actually articulate the formula of probability of A times probability of B given A. I just say multiply and adjust for replacement. Like you're just going to take these two as 2 individual events, you're going to multiply, but you're going to adjust for replacement or not. So another way I could do this problem is I could say, let's draw 2 cards with replacement. Well, what that means is that when I draw 1 card, I'm going to put it back in the deck. And so the deck's not changed at all. These are going to be independent events. So I don't have to compensate for this like subtracting 1 from the total. This is just simply going to be the probability, if I want the probability of a fish and a bird again, but I'm replacing the card. Now it's going to be 6 out of 24. That's the probability of the fish times the probability of the bird, which is still 6 out of 24 because the totals didn't change. You see the difference between the two. So a lot of times I'm not like formulaically thinking about this. I'm just conceptually thinking about this. How do I adjust that second fraction for what happened previously? So let's try one more here. What's the probability that I draw, let's say I draw 3 cards and I'm going to do without replacement. And I want to know the probability that I draw 3 4s. Now, again, the word and isn't in there, but it's implied. A 4 and a 4 and a 4. If you can, pause this video and see if you can write down the answer before I do it, and then start again, okay? 3 4s. That means there's 3 events. That means I need to build 3 fractions. So I've got 1, 2, 3 fractions that I'm going to build, and they're going to be multiplied together. So let's go the first. I'm going to draw a 4. How many 4s are there? There are 4 of them. So I'm going to do the first probability is going to be 4 out of 24. Now, I assume that I got the 4 I was looking for. So what happens is one of these 4s gets crossed out. Now I'm going to draw another 4, hopefully. How many are there over the total? Well, now there's only 3 4s. And what else changed? The total changed. I don't have 24 cards anymore. I got one of those 4s out, and so now I've got 23. Now what happens on then I get one of these. I get that 4, I cross it out. Now how many are there for my third? There's only 2 left. So now I'm going to build a fraction that says 2 out of, and the total changed again. I pulled one out, so now I'm at 22. All right, so you can kind of see how this is working and how you're building these fractions. When it's in fraction form, often you're building it yourself. Now, one last kind of variation of this, I could give you a problem where the fractions are already built for you. When I say the probability of something is 23 or 0.23, that indicates that I've already built the fraction for you. You don't have to do this how many ways out of the total. That is the division of how many ways out of the total. It's done. Okay, so let's say I have a problem that says the probability that, let me write it out in English. Let's say the probability that I own a dog is 20%. Let's do it in decimals. Let's go is 0.23. Of all the dog owners, 4.45 of them, of the dogs, have fleas. What's the probability that I find a dog owner whose dog has fleas? Okay. So this is, again, another implied and problem. It's a dog owner and the dog has fleas. This is going to be a multiplication problem, but I've already built all the fractions for you. So all you have to do is take the decimals. So I want a probability of getting a dog owner, so 0.23. And then of those dog owners, 45% have fleas. So what I've done there in the language is I'm telling you that this is already a given that probability. Like I've already limited you to only all the dog owners, and these are the ones of the owners that have fleas. So all I have to do is multiply these together. 23 times 0.45. Okay, and that's going to be your probability. Now, what if I change this problem and I say, what's the probability that I get a dog owner whose dog does not have fleas? This is where we're coming back to that complement idea. So if 0.45 have fleas, how many don't have fleas? How are we doing that? We're taking 1 minus 0.45, or 100 minus 45%. So that's going to be a 0.55. Notice that 0.55 and 0.45 add up to 1. That's 100% of the people, or the dogs. So 0.45 don't have fleas. So now if I want a dog owner, that's going to be 0.23. And that whose dog doesn't have fleas, that's going to be 0.55. And you multiply those out to get your answer. All right, so a couple different problems. Cards, where we're replacing or not. A lot of problems deal with marbles or die rolls. There's some table problems with given that examples where you're going to limit to the column or the row. And then there's some problems like this where they give you the percentages already built, and all you have to do is multiply. But be careful with the language. If I, in the problem, say 45% of the dogs have fleas, and I'm down here asking for no fleas, then you have to do that subtract from 1, that complement idea. All right, try some of those, and we'll come back for section 3.2, at least problems.